This conference will now be recorded.
So very good evening, students. Today we are discussing numerical problems from magnetism and electromagnetic chapter part. Actually, we have picked up various questions from previous years JEE papers. So we'll solve today also few more problems on this chapter. So let's start our discussions. So the first problem is a moving coil galvanometer has resistance 50 ohm. Okay, so you can see here so moving coil galvanometer has resistance 50 ohm. It indicates full scale deflection at 4 milliampere current. So what does this mean? Full scale deflection. If you have a galvanometer, when the needle shows full scale deflection, that means it goes either way up to here and here. Okay, full scale deflection. That means galvanometer can allow you maximum this much current. So we can say Ig is equal to 4 milliampere or 4 into 10 to the power minus 3 ampere. So this is the current through the galvanometer. This is the maximum allowable current or allowed current through the galvanometer. And galvanometer resistance is already given, that is 50 ohm, as you can see. Now look, we have to convert this galvanometer into the voltmeter using a resistance Rs, or simply R we can say. So the maximum voltage that can be measured using this voltmeter is how much? Let me draw this figure. Suppose you have galvanometer and associated resistance Rg. Okay, now along with this a high resistance R has to be connected to get a galvanometer, to convert a galvanometer into voltmeter. Okay, this is the way. So when the current flows through this, suppose total current is I, but how much current will flow through this? Since this R is in series with Rg, so whatever current flows through this galvanometer will pass through this also. So the voltage drop across this will be the voltage drop across this galvanometer plus across this resistor. Okay, R. So R is suppose here 5 kilo ohm. Here it is given Rg is 50 ohm and this is 5 kilo ohm. Okay, now we can solve this problem. So V will be actually V of the voltmeter will be Ig into Rg plus R. So Ig we know 4 into 10 to the power minus 3 ampere. Rg we know 50 ohm, and this we know 5 kilo, that means 5000 ohm. Okay, so if you do that, so you'll get 4 into 10 to the power minus 3, and this you can take nearly 5050, that means nearly you can take 5000 only, nearly 5000. Okay, just for checking the approximate values. So this will go with this, so it will be around nearly equal to or close to 20 volt. So this is the answer. It is here. Even if you multiply like add with this 5000, this 50, it is not going to change much. Okay, that's why it is all right here. Okay, so near around 20 volt of the voltage you can actually measure through this galvanometer. Okay, I hope I am clear to you. If not, please just look once again. So what were the parameters given for the galvanometer? Moving coil galvanometer has resistance 50 ohm and it indicates full deflection at 4 milliampere current. That means this is the IG. A voltmeter is made using this galvanometer and 50 kilo ohm resistance. So here we have to remember whether this 50 kilo ohm can be connected in parallel or series. That is the crucial point we should remember. Otherwise things were fine. Okay, so now let us go to the next problem. So this problem is also very important, and in fact the problem I have discussed just right now, it has been asked in JEE Mains 2019. The previous problem was, in fact today's almost all the problems I have picked up from JEE Mains 2019. Okay, almost all the problem today we will be discussing from 2019 paper JEE. So look here, in this case, a circular coil having n turns and radius r carries a current I. It is held in the xz plane. I'm just supposing this is z axis, this is x axis. So the plane is circular plane is like this. Okay, this is okay, and perpendicular to this will be actually the y-axis. Anyway, this is in the xz plane. So this circular loop or circular coil has n turns, and the magnetic field is applied this way, and the torque on the coil due to the magnetic field is what? We have to know that this is a circular coil which is held in the xz plane. Suppose current is flowing in the anticlockwise direction. I'm just supposing it. So the magnetic moment, torque actually can be obtained by M cross B. M is magnetic moment and B is the magnetic field present. Okay, so here M will be, if the current is flowing in this way, the M will be in this way. Okay, that is for sure. And since the torque on the coil due to the magnetic field, look here, torque is along z axis, sorry, this M is along z axis, M some k cap cross B is along y, I direction. So k cross I will be actually M cross MB j cap. Okay, MB j cap. So it will be along the j cap direction. Okay, j cap direction. But anyway, you have been asked to find out the torque alone, magnitude of the torque, since directions are not involved here in the options, so don't bother about it. So only thing is that you have to find out M into V. What is M? M is actually magnetic moment is current into area. So area of the loop is pi r square, and what is the current? Current, there are n turns, so n into I into pi r square. This is actually the magnetic moment, and magnetic field is given as B alone. So we can write torque is equal to mb, where m is, and b is as it is. Okay, so finally the answer is becoming n pi I r square into b. So magnetic moment torque due to this field. Okay, anyway, pi r square by, just a minute. So yes, so n into I, so mb sine theta. Okay, so ni, yes, actually our answer is correct. Our answer is correct here. I hope I have missed typing pi over here. Okay, let me check in the question itself. Yes, there is a typo over here, so there will be one pi along with this option, so that would give you the one we get. So here pi is multiplied, so we have got n I pi r square b. So this is the one. Okay, so this B will be the correct option. So here actually the problem was nothing. Only thing you need to know the M cross B. That means what is magnetic moment, what is B. B is already given in the x direction, and M is I into A. I means current into A, area of the loop, and I is the current. Okay. All right. So we'll move on to the next problem. Okay. So this is another interesting problem. We'll try to first read the problem and then we'll solve it. So the problem says that a magnetic compass needle oscillates 30 times per minute at a place where deep is given as 45 degree and 40 times per minute when the deep is 30 degree. B1 and B2 are respectively the total magnetic field due to the earth at the two places. Then what is the ratio of this B1 to B2 is best given by. So it is a very nice problem. You can see, first of all, let me tell you, suppose there is a place on the earth, okay, on the earth, where you place a magnetic needle, okay, where you place at the deep angle 45. First was placed like that. So then it was oscillating. Oscillating means frequency. So it is oscillating per minute. 30 times oscillation, 30 times. So we can find out oscillations per second, which is actually frequency. So oscillations per second means frequency. So yes. So this will be per second, and that means the time period is 2 seconds. Actually this frequency and time period, they are reciprocal to each other. So we have got first time period, and similarly when we keep the same compass needle at an angle of deep 30 degree. For that case, the oscillation is saying that 40 divided by 60, and similarly we can convert into time period. So 6 by 4 second or 3 by 2 second. Okay, so we have got the time period for both the places. Now we'll see, is there any relation between the magnetic field time period with the yes, so with the deep angle, etc. We'll see. So we have got T1 and T2. Now we have to find out, see B1, actually at the place B1, this is the angle of deep. That means actually we can write the horizontal component of the magnetic field 1 or the place 1 is B1 45 degree. That means cos of cos of 45 degree means 1 by root 2. So it will be B1 by root 2, B1 by root 2, BH1. That means it is actually the horizontal component of the magnetic field at the first place, and horizontal component of the magnetic field at the second place is B2 cos of 30 degree. That means B2 cos of 30 degree means root 3 by 2. Root 3 by 2 into B2. So after getting this, what is next? The next is that how the time period varying with time period, how the time period is related to the magnetic the magnetic horizontal magnetic field. The magnetic needle has time period. See, time period 2 pi root over sorry, this is capital M into BH. So the time period is actually given by 2 pi root over this by M into BH. Okay, so this is the relation between the horizontal component of magnetic field, then magnetization M, and also the time period of oscillation. So in this case, we are seeing that the T is directly proportional to, sorry, inversely proportional to root over BH. Okay, this is the proportionality relation we have where M is constant. Now what we can do from this proportionality relation, we can actually write T1 by T2 is equal to root over sorry, this is not square, B1H and B2H. So T1 by T2, T1 by T2. So this will be T2 B2H, square root of B2H divided by B1H. Now we know the values of B1 and B1H and B2H. Okay, so B1H and B2H, and this we have to apply. I'll just take the next page also, or let me go to the last. So what are the things we have got? We have got T1 to be 2 seconds, and then T2 that means the time period of oscillation is 3 by 2 s. Okay, and now we are getting T1 as T1 by T2 or T2 by T1. Let us write T2 by T1 or T1 by T2 itself. We can write T2 by T1 B1H divided by B2H. Okay, so B1H again we know. B1H means so B1 is means BH1 is equal to BI cos of theta. Here theta is 45 degree and for the other case 30 degree. So now if we just put this here and here, just make it square both side make square, because we need to get B1 by BH only. Now B1H and B2H these are, see, B1H is actually B1 by root 2 and B2H is actually B2 by H is B2 over H, actually this is root 3. It was 30 degree. Cos of 30 degree means root 3 by 2 into B2. Okay, so if we put this here in the square part, then we'll be arriving to this point that B1 by B2 will be if we put the values, finally we'll get like this, and if we further calculate and see things, then it will be 0.689. Okay, so this will be, I'm sorry, not 9, we are going up to here. So 0.7 B1 by B2 is equal to 0.7 we will be able to get. So what were the turning points? The points were that you have to find out the relation between time period and horizontal component of magnetic field. So and along with the oscillation part. If you are able to do that, then B horizontal component, that is total magnetic field into cos theta, the angle of dip. So B1 is, that's why I have written B1 cos of 45 degree, and B2 I have written B2H, I have written B2 is B2 into cos of 30 degree. Okay, so those we will be putting it here, and then if we simplify to get B1 and B2, then we will be able to get the problem. Okay, so we'll move on to the next problem. Next problem is the fifth one. So in this case, the answer is this one. So the fourth problem we'll solve here. The fourth problem says a paramagnetic material has 10 to the power 28 atoms per meter cube. Its magnetic susceptibility at temperature 350 Kelvin is 2.8 into 10 to the power minus 4, and its susceptibility at 300 Kelvin you have to find out. So for a paramagnetic material, the susceptibility is given by C by T. Chi is equal to C by T, where this is a constant quantity. This is a constant quantity. So we can write that chi is inversely proportional to time. Okay. Now see, if I have paramagnetic substance at 350 degree for which the susceptibility is given, then we will be able to easily find out this value if you want to find out, or otherwise directly what we can write is, you can write x chi 2 by chi 1, chi 2 by chi 1. You just take the ratio. Chi 2 is 1 by T2 and chi 1 is 1 by T1, so it will go up. So T1 by T2, that means 300 divided by 350. Okay, so this is 300 Kelvin divided by 350 Kelvin. We can simplify it a bit. 6 by 7. Okay, 6 by 7. Excuse me. So chi 2 will be actually 6 by 7 into chi 1. Chi 1 is given is this much. So 6 by 7 into 2.8 into the power. Okay, so we have actually obtained the value of chi 2 at susceptibility, at temperature T2. So yes, so This is 2.8 into 10 to the power 4 into. Okay, I hope we have done some mistake. Okay, so T1 is 350. That's why the answer was not coming. Okay, so this T2 is 300 and T1 is 350. Okay, so then it will be having some changes. 350 by 300. Okay, so this will lead to, okay, so 7 by 6 into chi1. Chi1 is 2.8 into 10 to the power minus 4, and this is unitless quantity anyway. So this would actually give you approximately, this will be 0.4, 0.4 and 6 kind of this. So if we just multiply this, 6 7 is 42, 4 7 4 28 4, so around 32. So yes, so there will be some factors obviously, and this will be 10 to the power minus 4, and this is the thing. No, see, there are three. 1 2 3. So here 1 2, so 3 2 3.2. So 3.2, 3.2. So see, you can see 3.2 is only this much. I have just done its approximate calculations. So from there also we are getting that 3.2 is an option given in the problem. So this will be the correct answer. If you just do with like if you just uh, do it properly, the calculation you may get the whole factor like this: 3.2 into 10 to the power, so 2.3 to 2.32, sorry, 3.26, 7 into 10 to the power minus 4. So that decimals may come if you do the calculation clearly. Okay, now we'll move on to the next problem. So this is also a very nice problem, but it is very simple problem if you can understand. So a bar magnet is by inserting it inside a solenoid of length 0.2 meter and turns 100 turns and carrying a current this. So that means you have length of the solenoid 0.2 meter and you have number of turns n is equal to 100. You have current given here is 5.2 ampere. Now see, actually when you keep a magnetic material inside to make it demagnetized, that means you are applying the magnetic field, you are applying in the current in such a way that the magnetic field is producing, or a magnetic field produced within the solenoid in the opposite direction of this magnet, bar magnet. Okay, the poles have to be just opposite. So in this case, the coercive field or coercivity, the coercivity is this. Coercivity of the bar magnet is H. So what is this H? Is the field strength, and that can be obtained by B by mu 0. And for a solenoid, you know what is B? B is equal to mu 0 Ni. What is this N? N, small n is capital N by L. capital N is 100 by N, sorry, capital, this is just opposite. Okay, let me just tell you. N by L, yes. Number of turns per unit length. So N by L. So it will be actually 1000 by 2 per meter. So this is 500 actually, 500. Okay, now see this N you have got, small n. Then what next? H is actually B by mu 0. That means this is equal to N into I. So N is anyway 100 by 0.2 into 5.2. So this 0.2, this 0.2 gets cancelled. This 26 into 100. Okay, so it will be 26 into, around 26 into 100. Okay, so the answer will be this one. I hope you have understood what you have to do. B is equal to mu 0 Ni. We know that for a solenoid, and you have to find out H. H means B by mu 0. So ultimately you have to calculate only this. Okay, so that's the answer for this question. Now we'll go to the next problem. This is also a very good problem, and almost all the problems are actually asked in JEE Main 2019. This is also from 2019 JEE Main. From JEE Main. So here look, there is a question: a square loop is carrying a steady current I, and the magnitude of its magnetic dipole moment is M. So the direction of the current is not given anyway, but there is a square loop, and there is a current carrying in the square loop. If the current carried by such a loop, so it will be associated with magnetic moment. That magnetic moment is given as M, which actually can be written as I into A. I into A means A is the area. Suppose this has length A, so we will get actually I into A square. This is the magnetic moment at the center of this. Magnetic moment is I into A square. I into A square. This is the magnetic moment for a circular loop. Now look, the length of the wire, okay, length of the wire is not changed, and current is also same, but the shape of the wire has been changed now. It has been changed to circle. Okay, we know 4A, this is the perimeter of this circle, maybe that will be equal to L. And what about this case if I say small r is the radius of this circular loop, which is made out of this square loop itself? So we can write 2 pi r is equal to also L. Okay, or In other words, we can just find out what is this uh, L by 2 pi. So what is L? L is again 4a from this we have got divided by 2 pi. So it will give you 2a by pi. Now see, the magnetic moment means what? Current into area. That is magnetic moment. So here, suppose the magnetic moment is A2. Sorry, M2. Magnetic moment is M2. So in this case, we'll do I into pi a square. Pi a square is the area of this circular loop. I is the current which is passing through the coil. Okay. So what is this pi a square? You have to find out that in terms of the small m and all. Okay. Anyway, so this is pi, not pi a square. This is pi r square. So what is r? You have to write it down. R is 2a by L. So 4a square. Sorry, 2a by pi. 2 is a by pi. Okay. So then you get, I into a square, let it be common. So pi goes up. So pi a square, sorry, I a square into 4 by pi. So this is I a square means again from here, I a square means here, from here, small m into 4 by pi. Okay. So the option is 4m by pi. So this first option will be correct option. Okay, so the answer is this one, 4m by pi. Okay, so we'll go to the next problem. The seventh problem. Magnitude of magnetic field at the center of hexagonal shaped coil outside this and 50 turns carrying current I in the units of this. So you have to find out a magnetic field for a hexagonal current carrying loop or coil, and coil has 50 turns. Let me tell you the situation. When the hexagonal is said, we have to take by default the hexagon is a uniform hexagonal. Uniform hexagon means it has all the sides equal, say A, and all the angles will be actually 60 degrees for ideal and uniform hexagon or hexagonal. Okay, so we know for calculating magnetic field for a finite length of the wire, what we have to do, the formula is actually magnetic field. The formula of the magnetic field is B equal to mu of the magnetic field I by 4 pi A. A is the, sorry, let me tell it, D, 4 pi D. So this distance is D, this much. This is D. This into sine theta 1 plus sine theta 2. Okay, so this is the formula you have to use. So here, see mu 0, you have to calculate the magnetic field in the unit of mu 0 I by pi. So this part we don't bother about. Now let us say this part 1 by 4d. Okay, and this part is sin phi 1 or sin theta 1 theta 2. So in this case, you know what are the sin theta 1 and sin theta 2? The angle this, okay, because I'll draw a perpendicular from this particular point, making this particular angle as half. So since the hexagon is uniform, this actually if you add the diagonal to the center, it will make each of them will make a equilateral triangle. Okay, equilateral triangle. Now if this 1 by 4d, see in this case theta 1 and theta 2, this is actually 30 degree for both, so 2 into half we can write sine 30 degree means. Okay, and what about this d, this equilateral triangle a, so this height is d, the d will be root 3 by 2 into a square, sorry a, root 3 by 2 into a, not a square, root 3 by 2 into a, this is the height. So if you put it here, look, mu 0 I by 4 mu 0 I by pi, this will keep as it is, so this will make you 2, so you get finally 4 d, 1 by 4 d. Okay, so what is this d, and there are actually n terms, so the here n has to be multiplied. So basically this d is how much, root 3 by 2 into d, root 3 by 2 into a is so from here actually d will be calculated, d is here, so it will be, so this is for only one, so this d I'll just substitute here, so 2 will be up here root 3a. Okay, again this has to be multiplied with 6 so that you get the for whole hexagon. Okay, so this 3 can make it root 3, so mu 0 I by pi into n means 50 root 3 by a means again 10 to the power minus 2, that means 10 to the power minus 110 multiply. Okay, so 500 into root 3, this will give you 500 into root 3 into mu 0 I by 4 pi, sorry only pi, mu 0 I by pi, this unit you have to calculate. This is simple problem. Okay, so for today we'll keep it here. We have already discussed some 7 problems, so you might be a little bored, so we'll take up further few more problems in the next class and then wind up this magnetism chapter. I hope you have understood this. I'll quickly say once again, so this is the formula for the magnetic field to find, like from the Biot-Savart's rule to find out magnetic field for a finite length wire. Okay, so mu 0 I by 4 pi d, d is this distance, okay, from the point of interest where we are calculating magnetic field, and this is the length of the wire. not this a by 2. It is actually the d is this distance, perpendicular distance from this point to the wire. That is the d. That's how you had calculated height of this equilateral triangle. And when there is a uniform hexagon, if you add this corners to the center, it will always make a equilateral triangle. And if you drop a perpendicular bisector to this angle, then you will get 30, 30. So that's why theta 1, theta 2 are 30 and 30, and d is this distance only, this height of the triangle. So rest of the things are nothing, just calculation. You might be expert in that. So with that, you'll be able to solve the problem. Okay, so bye for today. Thanks for your patience. We'll meet in another class, next class. So bye for today.